In this video, we're going to talk about random forests for ensemble learning. We'll talk about ensemble learning in detail later on. This comes through to you through my YouTube channel AINEXUS and the playlist Course on ML. I'm Dr. TV Geeta. Please do subscribe to this channel. The learning objectives of this video is to understand the concept of random forest, explain how multiple decision trees work together, learn bagging and random feature selection, apply random forest for classification and regression, and then evaluate the advantage, limitations, and applications of random forest. Random forest is a type of ensemble learning. It is many trees, one powerful model. So random tree is a supervised machine learning algorithm that combines many decision trees to make a stronger prediction. So the type is supervised. Tasks are, it can do both classification and regression. It's an ensemble method because it combines many predictions from multiple decision trees. The goal is to improve generalization and reduce overfitting. And so you have many trees, tree 1, tree 2, tree 3, tree 4. So you combine the predictions either through majority voting in the case of classification or averaging in the case of regression. You get more accurate predictions, stronger also. So why do we need random forest? Decision trees are great, but they have some problems. Random forest solves them by using many trees together. So limitation of single decision trees, there is overfitting. We already seen these terms. There is high variance, high bias, and when the tree is shallow, and unstable and less reliable, single trees. So how random forest helps? It reduces overfitting, reduces variance, improves accuracy, and makes it more robust and reliable. So the result is random forest takes many weak trees and a smart combination to get a one strong, accurate, and stable model. So what is an ensemble model? If we go further, an ensemble model combines predictions from multiple models, often called weak learners, to make a stronger, more accurate, and more reliable prediction. So it uses many models instead of relying on a single model, combines their predictions to get the final result, reduces errors, variance, and overfitting. So therefore, accurate and stable model. That is what is shown here. Examples of ensemble models are, lots of them are there. Bagging, which is also called bootstrap aggregation. It's an average or voting. Boosting, sequential learning, this is a weighted vote. Stacking, model stacking, and random forest, which we are going to discuss here. And instead of putting all our trust in one model, the ensemble model generally uses many models and takes the best answers. Remember, this is not necessarily about random forest alone. We'll be going into ensemble learning later on also. So how does random forest work? Let us look at that. So input data, you have a large training set. So you first do bootstrap sampling, create multiple random samples with replacement from the data set. You take the data set, take a random sample, keep the random sample back into the data set and choose another random sample like that. Then you build decision trees for each such sample. You grow a decision tree. At each split, randomly select a subset of features to find the best split. Then you get the prediction. So you have tree 1 giving prediction 1 and so on. And then you aggregate the results. So combine all predictions to get the final output. Classification, you will take majority vote. And regression model, you will find the average of the results. Why it works so well? It reduces overfitting. All these we have already seen. It's scalable also, and it handles complex data also. Okay, so data, many random trees, voting or averaging, and the best selection. So the magic ingredients here are the sampling, bootstrap sampling, and the random feature selection. So different data for different trees. That is important. Instead of using entire data set, random forest creates multiple random samples with replacement. That is when you're taking a training set, you will take one small sample set and replace it before taking the next one. That's why it's called bootstrap sampling. Each tree is a different tree sees a different version of the data, making the forest diverse and robust. Next is random feature selection. So you use different features for different splits. For example, at each split in a tree, random forest selects a random subset of features not training data, features, instead of using all features. For example, suppose you have age, income, education, marital status, credit score, loan amount, employment, and so on as features. At split 1, you will randomly choose some k features. At split 2, another k, and so on. This randomness in feature selection reduces correlation between trees and improves generalization. So bootstrap sampling makes trees different by using different data. Random feature selection makes trees different by considering different features at each split. Together, they create a strong, accurate, and stable model. Now, there are two powerful uses of random forest. One is classification, another is regression. So, used when the target variable is scattered out. We know everything that is for classification. So, you do input, you give the input data, you do bootstrap sampling, build multiple decision trees. Predictions, we've already discussed this. Predictions are given, and final prediction will be the majority vote. So, here you have two green, so it's given green. So random forest for regression, input data. Here we have used only bootstrap sampling. So you do the same thing that you do there, but build multiple trees. Each tree predicts a numerical value, and then you take the average of those values. So why both work so well? It reduces overfitting, improves accuracy, robust and stable, works on large data, and it is very flexible and powerful. So let's compare the two, random decision tree and random forest. Of course, decision tree, you have a single tree. The model is a single tree. Here you have an ensemble of many trees in random forest. In decision tree, data usage here uses all the data. Here it uses randomly selected subsets using bootstrap sampling. Then overfitting, high risk of overfitting if it's a decision tree. Here low risk. Accuracy, lower accuracy when compared to random forest. Here high accuracy. Stability, high variance, sensitive to data changes. Here there is low variance and more stable predictions. Training time faster here but slower here, but it can be easily parallelized. Interpretability, easy to interpret and visualize for human beings. Harder to interpret, but it's more accurate. Best use case, here small data sets, simple problems. Here large data sets, complex problems. So that's the comparison between decision trees and random forest. Then there is one particular evaluation here called out of bag evaluation or OOB evaluation. So it estimates model performance using data not used to train each tree. So how it works, for each tree, a bootstrap sample with replacement is drawn from the training data. Some data points are left out for that tree. Okay, you select it, but you leave out some. That is the out of bag data. Similarly, you do it for tree 2. Okay, and for prediction, each tree uses its out of bag data to predict. So aggregate the OOB predictions from all trees to evaluate the model performance. Why this is powerful? Uses only training data, no separate validation test is needed. Built-in cross validation for random forest, because we are using different things and you're already dividing the samples, provides an unbiased estimate of how the model generalizes to unseen data, fast and efficient. So true error is the unknown error. OOB error is an estimated error. Next is controlling random forest complexity. This is another important aspect. Complexity control helps prevent overfitting, improve generalization, and make models more stable and interpretable. So why do you want to control? Too complex means it overfits. Good control, better generalization to new data. Right balance, accurate and robust. So here you have the key hyperparameters that control complexity. So N estimators is the number of trees. So the number of trees in the forest. Effect of increasing the value, it improves accuracy to a point. Then saturates. It's more stable. So you can see the ranges here. Then maximum depth is another important part. So maximum depth of each tree, deeper trees, more complex, high overfitting risk. Minimum sample split. Minimum samples required to split an internal node. We have seen some of this when we're discussing decision trees. So higher values, simpler trees, less overfitting. Minimum samples leaf. Minimum samples required at a leaf node. Higher values, smoother prediction, less overfitting. Number of features considered at each split, that is maximum features. Lower values, more randomness, less correlation between the trees. So balance complexity, you will get underfitting means too simple, just right is balance, overfitting is too complex. You see that these concepts of overfitting and bias and variance comes in many places. We'll be discussing that. So this is how controlling random forest complexity is done. Now we'll see how Python can be used for both decision tree and random forest. We did not describe the Python implementation when we were talking about the video on decision tree. So the workflow is load the data. That is what is shown here. So here you see that you import the data, select train, test, split, and so on. And then train the model. So prepare the data and train the decision tree and train the random forest. Then evaluate, compare equivalent accuracy and visualize the trees. So model comparison, decision tree, single tree, easy to interpret. Typical accuracy will be of the order of 93%. But if it is random forest, typically it will be about 96%. With few lines of Python, decision tree gives explainable predictions and random forest delivers high accuracy and robustness. So that is the code that is given. And then the advantages and limitations. Advantages are high accuracy, reduced overfitting, handles high dimensional data. We've already discussed, so I'm not going into detail. Captures nonlinear relationship, little data pre-processing, and provides feature importance. We've already seen this. Limitations is computationally it's expensive, high memory usage, less interpretable, not ideal for very sparse data, biased towards features with more levels and tuning required. So these are the limitations and advantages. Then let's see some real world application. Healthcare. For example, predicting heart disease risk from patient data, finance, detecting fraudulent credit card transaction, marketing, predicting customer churn in subscription services, e-commerce, predicting product popularity and demand, insurance, identifying fraudulent insurance claims, manufacturing, predicting machine failure before it happens, telecom, predicting customers likely to switch to another provider, environment, predicting wildfire risk based on environmental factors. So these are some of the typical applications. We've seen this over and over in many of the slides. So basically, random forest adapts to diverse data and complex problems. That's the main thing. So making it to go-to algorithm for real-world machine learning solutions. Now let's look at the summary. An ensemble learning method, which is decision tree based on multiple decision tree, combines predictions from many trees for better accuracy, uses random samples and random subsets of features, reduces overfitting compared to a single decision tree, and can be used both for classification and regression. These are some of the references. These are some of the exercises, both short answer questions and descriptive questions. These are problems that I've given. 5 numerical problems and programming questions also are given, and then some mini projects, again student performance prediction, customer churn prediction, house price prediction. These are typical mini projects that is done in a machine learning course. So thank you. Please do subscribe to my channel AINEXUS and the playlist on course on ML. The next video we'll be talking about SVM, that is a supervised machine learning algorithm again, which is used basically for classification. SVM is support vector machine. So thank you.